The other thing that could be happening is I could have something bad going on in my torch here. It just occurred to me that this is exactly how the torch, well, with the exception of that tungsten looking really bad because of my horrible work the other night. This is exactly how the torch was when I got the unit. I haven't taken apart this part of the torch and looked at anything, and just now I happened to unscrew the cup here and realized that this is actually the tungsten stuck in there. And not only that, but when I pull the tungsten out, there's white powder all over this thing. It almost looks to me like there's some corrosion inside here. So I really should see what the heck's going on with this tungsten. Who knows, there could be a short right inside that cup there. There's got to be a way that this comes out, right? It's probably supposed to slide right out. Yeah, I'm no expert, but I'm pretty sure this is not supposed to be permanently welded in there like that. Oh, that's interesting. Look at the crud. It's falling off. That's not good. Alright, got that piece off. And now this can come out. Okay. Alright, I don't think the tungsten's supposed to look like that. Now that damage right there may have been all me because I was trying to weld the other night, and I was expecting the high frequency to do its job, and I kept putting it closer and closer, and I wasn't doing a very good job of being able to visualize what I was doing. So I kept basically, instead of scratch starting, because again, I didn't think I would have to scratch start, I just kind of kept pushing the tungsten down until I would draw an arc and then pulling up. And that, I think, is what was causing this, what caused a lot of this damage to the tungsten here. Alright, so I cleaned up this tungsten, and I ground a not so great point on there because I'm not really looking to weld with this tungsten. I just want to do some experimentation with the high frequency. And I cleaned up all of the white powdery corrosion that was on the outside here, and I cleaned out the inside of this piece, and I'm ready to put it back together. So I took this out, I just screwed this back in. That's pretty self-explanatory, but I'm not sure. I didn't make a note to myself which way this goes on. There's a wide end here. If I take this apart, if the wide end goes in here, it almost seems to obscure these holes where the shielding gas is supposed to come out. So I think it's supposed to go on this way. Oddly enough, I can actually put it on either way, and it works correctly as far as that when I now tighten the back cap here, it pinches down on these fingers that actually hold the tungsten. So I could review my video of when I just took it apart, but I'm actually not going to assume that it was even correctly put together when I got it. I mean, more than likely it was because they were using it. But maybe they were using it and like thinking, geez, this thing doesn't work really well, let's get rid of it. And they sold it to me. Well, as luck would have it, when I bought my milling machine, the cabinet that they included with it, with all of the stuff that they said went with the milling machine, also had several other goodies in it. What was also sitting by the cabinet was a large ESAB welder. And apparently whoever bought the welder, because the welder was gone when I went back to pick up the mill, didn't notice that in the cabinet there were several items that were for the welder. So I ended up with this little box of trinkets here, this box, this, and some other stuff. So I got some consumables. The only question is I have no idea what the torch was on that thing. Now, as luck would have it, this is an ESAB torch that I do have for my welder. So I'm wondering whether or not this will work. So this is an HW20, and I think, I might be wrong, but I think these are actually sized, these components are sized by this, by the size of the torch and not necessarily by the manufacturer. So for instance, maybe, yeah, so like that cup fits on there. So I have no reason to believe that these other cups won't also fit on there. So I've got a few used cups here. These are brand new cups, 13 N09s, nozzles. Huh. Yeah, we have 4 in there. I got this, another one of these end cap things. This looks shorter than the one that I had, but that's not going to fit on. That's actually a different design altogether. See, that's got the O-ring on this part, goes down inside there. So that's not going to work on there. But look at this little stubby cap. That actually looks... Well, no, that doesn't work. There are no threads in there. Well, they are, but they're way the heck in there. Alright, so I've got 2 caps of different design. Neither of them fit this torch. That's wonderful. Alright, so here's the original one that I have, and here's the little short stubby one, and they look so close that I was like, well, wait a minute, maybe I just didn't try hard enough, and that's what it was, because if I give it a little push to compress that ring, that O-ring, this one does screw on. So this little short stubby one fits my torch. But this is a completely different animal. You can actually see the diameter of this threaded part is actually larger, so I'm not sure what size torch that goes to. So the cups all seem standard. This must be little lengths of filler metal. Okay. And we got several of these little nozzle deals here, which, well, oddly enough, they appear to be identical. They seem to screw in there just fine, so I think these nozzles are good. I'm assuming that's a nozzle. We got several sizes. Ooh, that's a big tungsten. Look at that tungsten. Oh my. That's thick. Look at this one. That's thin. What are we on, Sesame Street? Thick. Thin. Alright, so that's why we got all these different size things in here. And looks like they didn't throw anything away. It's all these little, oops. All these little balled up tungstens. So probably these guys were probably doing a lot of aluminum work, maybe? I don't know. Oh, so we got more of these things. None of this tells me anything about which way that torch goes back together. Ah, of all sites, the Artec welding site from the UK comes to the rescue. I just put in TIG torch components in Google and then selected images, and I saw this came up, and it happens to be Artec. So I just thought it was kind of funny that it was Artec, because those of you who follow Double Boost, his channel, John, I believe he is sponsored by Artec welders because he started using them, and I think he's a big fan of them. But anyways, they got a nice little picture right here, diagram, and it's got all these things, and I'll try and remember these. That way I can start calling these things what they really are. For instance, this thing I was calling a nozzle is actually the collet body. And then that, I probably would have called it a collet if I didn't already do so, because it looks like the way it's designed. I could see that the little heavy end is at this end. So that makes sense. That's how I thought it would go, because again, like I said, if I flip this around, that heavy part right there tends to block the holes where the weld shielding gas is supposed to come out. Of course, this is a cup. I knew that. I didn't realize this little white piece right on here is actually a heat shield. So there's a doohickey on here that I thought was part of the actual torch, that little white piece. Apparently that is supposed to be able to come off. Well, I'm going to leave it on there, but apparently this comes off, so you can change this to a different type if you want to put a gas lens. If you want to convert this torch to a gas lens, which is this thing up here, which uses a different type of cup, then you would change that heat shield also. Maybe this one doesn't come off. Maybe you can't put a gas lens on here. I don't know. Hey, that's part of being a noob. All right. But more importantly, I figured out how my collet goes, so I can put this back together and go back to my diagnosis of my HF problem. Okay, so we know we want clean metal for TIG welding, but again, this is just for testing purposes. So I've got this piece of plate steel here, and I've also got my tungsten stuck out way too far. Okay, it's probably about a ½ inch. That's just so I can really visualize better how close I am getting to that steel, and I want to see whether or not we can get that high frequency to jump without actually touching. Also, I'm hoping that if I keep my current control all the way down, my amperage control, if I keep it all the way down, I should be able to just step on the pedal enough to close the contactor, initiate high frequency, and not have to worry about actually drawing an arc. If I'm wrong about that, I'm going to flash the crap out of my eyes, and I will have to then go with plan B and wear my helmet the whole time I'm trying to diagnose this thing. I'm going to recreate what I had the other night. I coiled the torch cord cable back up into a coil just like it was the other night. I'm going to run my cooler even though I don't intend to weld, just because, again, if that's something that's a factor, I want to be able to isolate that. So the only thing that's going to be different than the other night, I got a different piece of metal obviously, is the fact that I cleaned up the torch. So we'll see whether or not that makes a difference. Hopefully over all this background noise, which is the huge cooling fan on the welder and the water cooler running behind me, when I step on the pedal you'll hear a loud click. That's the contactor closing, and then you might hear a sizzling noise. That's the spark gap. It's a hiss. It sounds like shielding gas, but I don't even have the gas turned on. That's actually the spark gap. So I've got my amperage control turned all the way down. I'm going to put a glove on just because I got the heebie-jeebies. Yeah, just flashed myself. All right, so I'll put the welding helmet on. So the way that I ended up flashing myself is that I accidentally touched the tungsten to the plate. If I touch the tungsten onto the plate and pull it up just a tiny bit and engage the pedal, you see there's no high frequency jumping there from that little tiny amount. I believe I should have something going on there, and I don't. So what I'm going to do next is I'm going to uncoil my cable. I've now uncoiled my TIG torch cable. Let's see if that made any difference. Nope. Now I've unplugged my water cooler, which is not a good idea, but I'm only going to do this for a very short second. By unplugging the water cooler, I've removed the ground of the cooler. So if all of my HF is bleeding off through that coolant circuit, it means that the overpriced, expensive ethylene glycol that I put in there is conducting too much. Or I don't have a strong enough HF in the first place to override what's being bled off by the cooling circuit. I'm actually hoping this doesn't work, because I really don't want that to be the answer. Yeah, that's not it. For anybody who was wondering, I had the intensity, the high frequency intensity control at about 50. I've now cranked it up to about 100. So just for the heck of it, we'll try that. And if that doesn't work, then I'm going to go on the assumption that it's in the welder itself and not the TIG torch. that little arc you just saw there, that was just, again, I accidentally touched the tip, so it's like a scratch start. All right, I guess I should have said this at the beginning, though. If you're on this video right now because you're diagnosing your own high-frequency start problems, the situation with mine is that I've got spark gap activity when I close the contactor. So I know the high-frequency circuit is trying to work. It just doesn't seem to be making enough high frequency, or the high frequency is being bled off by a short or something going on inside the machine. But if on your machine, if when you step on the contactor and you have that switch in the continuous, the high frequency switch in the continuous position, when you step on that contactor, if you don't have any spark activity here, you've got something going on more on the primary side of this circuit. So what I would do in that situation, if it were me, the first thing I would do is verify that you're getting 120 volts going to that high voltage transformer that generates the high voltage for this circuit. So if you don't know where the high voltage transformer is, what I would do is I would follow, there's actually a wire right here, okay? This wire right here is going to, it's going through a hole in this fiberglass board right here, and this is going to go to that transformer. Almost positive. Because this is the output side of those capacitors going over to the intensity control. So this is the input side of that capacitor. Okay? This is the spark gap. So this has got to be, this wire has got to be going to the secondary of that transformer. Once you locate that transformer, you should be able to locate the primary winding of that transformer, those wires. Of course, this is all assuming that you've got a schematic. If you're lucky, you still have a schematic on your machine that's legible. If not, there's plenty of schematics online, and they may not be exactly like the one that's in your machine, but they should be close enough for you to do a diagnosis. So you go to that transformer primary, and when that contactor closes, you better have 120 volts there. If you have 120 volts there, then I would disconnect one of the wires to the primary of that transformer, and I would measure the primary winding of the transformer. And if you have infinite resistance, it means your primary is open on that transformer, and well, you get a big problem because you get a bad transformer. Then you got to get into, gee, you know, can you find a good used transformer to replace it? Could you put a microwave oven transformer in there to replace it? That's an interesting thought. Of course, maybe it wouldn't work at all. Maybe it would work too well and blow out your caps. Who knows? So, but that's a whole nother kettle of fish. So we're going to go on the assumption that if you're like me, you're lucky enough to actually have some activity going on over here. So the next test I'm going to do is I'm going to actually kill the shop light that's right in this area, and I'm going to energize the circuit. And what I'm going to look for, obviously this is going to be pretty bright here with the lights out. I'm not going to shut off all the lights, but I'm going to see whether or not I can see any hint of flashing behind the board here, which would indicate, or down in here in this gap, to indicate that there's high frequency jumping to ground somewhere behind there where it shouldn't be. Well, nothing there. Now that doesn't mean that I don't still have garbage inside there, inside that coupling transformer area that could be causing a problem. But I'm going to go to another likely suspect, which would be these two capacitors right here. Now, interestingly enough, I made the incorrect assumption that if I have spark happening at this spark gap, that means my capacitors are okay. Because remember, the way the circuit works, if this capacitor can't charge and discharge, we're not going to get spark here. Here's the problem. These are high voltage capacitors. So they could have a type of failure where they're breaking down and internally arcing. and causing a problem where they're not able to come up to as high a charge as we really want to see on them, but still charge and discharge enough to cause this action over here with the spark gap, but not enough to cause the high enough intensity so that we need to work the torch. So one of the diagnostic tricks that I've seen on several forum pages talks about removing one of these two caps at a time. Yeah? Well, pardon the interruption, but it's Sunday morning and the wife was cooking breakfast. Now, she just alerted me to the fact that something happened with the stove. The stove stopped working. Well, initially I thought, did I trip the breaker? Because the outlet that I'm running my welder off of is a 50 amp circuit for the range that I tapped into and put an outlet down here for this. It's kind of a temporary measure, and I figured, well, as long as I'm not doing any heavy welding, I can get by with a 50 amp breaker, and as long as nobody's using the stove, I can get by with a 50 amp breaker. Here's the interesting thing though. It didn't trip the circuit breaker. What it did was screwed up the electronics. It's one of those, you know, digital clock, soft touch, on off type of circuits there. So when she was cooking, it suddenly stopped cooking, and when she would press the button, it would just say off. Now, my theory is what happened is this thing is generating enough electrical noise on this circuit that it actually scrambled the computer in that stove. So all I had to do was shut the breaker off and turn it back on, which reset the computer, and the stove is now working. So the stove never lost power. It never tripped the breaker. So it wasn't an overcurrent issue. It wasn't like I taxed the circuit. It's that this HF bled into that circuit. That's my theory anyways. All right, so I'm going to have to forego any further live testing of this circuit until after breakfast. But let's talk about the two caps here. So on various forums I saw them mention that one of the ways to diagnose if you've got a bad cap is to take one of the two caps out of circuit and basically try and see if it works. If it works, then you know that cap was bad. And the idea being that it's making an assumption that you have one cap that's good and one that's bad. So if you could lift one cap out of circuit and make the circuit work, the assumption is that it's going to just run okay off of one cap. But that would be only for a very short test period, because now that one cap is being burdened with all of the voltage in the circuit. So not only that, but the capacitance has changed. So you're detuning your LC circuit there. So anywho, I could do that, but just for giggles, I think what I'm going to do, I'm going to pull my two caps and I'm going to test them on my capacitance tester. Now the capacitance tester cannot go up to the voltage that these things can handle. So you know, an ideal capacitor checker for these would be able to generate the kilovolts that these things are supposed to operate at. So it's going to be kind of a test, but mainly I want to look at whether or not I see anything uniquely different between the two capacitors, and also I can test these against the two spare ones that I have from the other welder that I scrapped. Alright, so let me give you a tip when you're taking these capacitors out. Obviously you got to take off the nut, and there's a little washer into each one of the nuts. You don't want to lose that. The only one that didn't have a washer was one of these posts didn't have a washer because there's an I terminal that goes to the wire that comes from the secondary of the high voltage transformer. And then behind the capacitors, where they mount to that fiberglass substrate, there were these little washers here. So the screws go through, the mounting screws go through the front of the capacitor and then pass through this washer, which acts as a little bit of a standoff and keeps the back of this capacitor from being completely on the substrate. My point is, I didn't realize these suckers were behind there, and I luckily, when one of them dropped out, it landed and stuck behind the capacitor, that big can capacitor below it, and I was able to fish it out with a magnet. Once I realized that there was one there, I made sure that I was able to account for all four and unscrewed them in a way so I could carefully reach behind there and make sure that the washers didn't fall, because they can easily fall down into the abyss, and you know, your luck's not going to be that good that they're going to fall out of the screen in the bottom of your welder. No, they're going to fall somewhere you don't want them to be, and they conduct electricity, which makes them nasty in the wrong place. Alright, so let's take a look at these caps. Well, these are genuine Miller. Look at that. Miller Electric Manufacturing Company, Appleton, Wisconsin. There's a part number on here, is 01-602. I believe that is an obsolete part number. I believe the new part number is different, but don't quote me on that. But again, a quick search of the internet will find you several sources for these replacement capacitors. Here's the thing that I think is really interesting, that Miller apparently decided that they would have these capacitors made for them by the Cornell Dubilier, D-U-B-I-L-I-E-R, capacitor type. Okay, now here's what I think is dirty pool. What Miller did was they had these capacitors made by this company for them, because Miller's not in the business of making capacitors, and then Miller silk screened or had them silk screen on this information here. But you see these little boxes on the top here? These little boxes would have been where the manufacturer of the capacitor, this Cornell Dubilier company, would have put all the pertinent information that we would need to know about this capacitor so we could source it from someplace else. For instance, the voltage rating would have been right here. KC stands for kilocycles, which is now known as kilohertz. So that would be the frequency that the capacitor is designed to operate at. Looks like this might have been amps, and microfarads, MFD for microfarads. So if this wasn't all covered, we could actually source this. Now, the dirty little secret about these is out. It's all over the internet. It's well documented that these are 0.002 microfarad caps, and I believe they were 6 kV was what they were originally rated for, either 4 or 6 kV, but you can find it online. But the general consensus is that at this point you want to replace these with something even more robust. We don't want to mess with the microfarads. We want to have a higher voltage rating if possible. So you can put a higher voltage rated capacitor into a lower voltage rated, but you can't go vice versa. In other words, a 10 kV cap can be put in the place of a 5 kV cap. In fact, it's going to give you actually more longevity, as long as you can physically fit it in there. But you want to have the microfarads stay the same. On the other hand, you can't take a 5 kV cap and put it in a 10 kV to replace a 10 kV, because the 10 kV is there because the circuit's, you know, got more than 5 kV of voltage in there, so that cap will fail quickly. And as a matter of fact, if you put too low of a working voltage cap in there, it will fail violently. Would be the best. Violently would be the best way to put it. All right, so just do a quick little check of these caps physically. I do not see any cracks or anything to indicate that there's... I got a little dimple there, but that's probably just when they poured this epoxy in. This one looks the same. This actually says it was inspected. Oh, that's neat. So they are marked that they were inspected. These actually physically look like they're in pretty darn good shape, but I'm wondering what they what they actually look like electrically. A quick word about testing capacitors. If you have a digital voltmeter that has a built-in capacitor checker, it's going to be pretty useless for testing this type of a capacitor. The only thing you can really check with that is you could check the value of the capacitor, but it's actually giving you the value of the capacitor when the capacitor is really not doing any work. The problem with the type of failure that you can run into with this type of capacitor is where it's breaking down under working voltage. So in order to simulate that, you really need a much more elaborate tester, something along the lines of a Z-meter. This is a Sencor model LC75 capacitance inductor analyzer. What this will do for me is this will allow me to measure the capacitance, but it'll also allow me to check something called leakage on a capacitor while it's under voltage. The problem with this analyzer is that this analyzer only goes up to 600 volts. So you can see this knob over here is leakage voltage. So just for the heck of it, I'm going to test the capacitance for starters. So if I check the value, alright, it's measuring at around 1980, 1990 picofarad, which in actuality 2000 picofarad is 0.002 microfarad. To convert from microfarad to picofarad, you move the decimal point 6 places to the right. So if we take 0.002 and we move it 3 to the right, that's 2, and if we move it 3 more to the right, that's 2000. So in actuality, that is not that out of line. As a matter of fact, I also did not zero my leads since I tried this earlier, because this is the second time I'm testing these. And that one's measuring 1990, kind of on the edge of 2000. So capacitance wise, they seem to be measuring okay. So now I'm going to do a leakage test. So I put my leakage voltage. In this case, I'm going to put it up to the maximum this unit can provide, which is 600 volts. The red flashing light indicates to me that when I press this leakage button, 600 volts will be applied at the test point. So I wouldn't want to be doing something like, oh, I don't know, holding them on with my fingers like this. That would be unpleasant. I'm going to get some alligator clips so I can get around the problem of these mini test clips not fitting. So this is what I was talking about as far as a capacitor checker built into a digital voltmeter. A lot of these kind of DVMs have a capacitance checker, but you're limited to the capability of something like this. You can't do a leakage test on the capacitor for leakage current. There's only a 9-volt battery in there. But if I put this on this range right here and then I press this selector, I can actually get it to go into capacitance mode, and right now it's just showing the lead capacitance, which is in nanofarads. There we go, that's microfarad. .0022 microfarad, and I don't know about the same 0.0022 microfarad. So again, what did I show? I showed that, yeah, these are measuring the correct value of capacitance, but this does not prove anything, because maybe they don't start to break down until, you know, a couple thousand volts are applied to them. So again, I'm only going to be able to put 600 volts across this thing. That might not be enough to get it to break down. But I am interested in what the leakage current that it measures is going to be. If there's a big difference from this one to this one, that might be an indicator of a problem. Alright, so I am going to set this leakage range to all other capacitors. And we're going to hit the leakage button. And at 600 volts, there's virtually no leakage whatsoever in there. Let's look at this one. You also run the risk of there being a charge on the capacitor after you take it off the charger. I mean, after you take it off the tester. So it's not a bad idea to discharge the capacitor. after you take it off the tester, especially the aluminum electrolytics. They really store charge. Virtually the same. Well, I went upstairs to my other shop and I got my other Z meter. This is the Sencor LC102 auto Z meter, and this one can go up to 999 volts for the leakage test. So I decided, just for the heck of it, to do a leakage test on the caps using this meter. Verified the value, 0.002, and if I do a leakage test on these caps at 999 volts, they still pass with flying colors. They actually are showing 0 microamps of leakage current. Then I went and I grabbed the 2 capacitors that I took out of the unit that I scrapped, and these are also original Miller parts. These were made by the Sangamo capacitor company. They clearly marked microcapacitor. Okay, but these have the evidence of leakage. Just for the heck of it, let's see what these test. Value is good. This capacitor is actually showing 1.28 microamps of leakage, and it's pretty steady there, so I would say that this cap is leaky. Of course, I don't know what the allowable leakage current would be for a cap. If we treated this as if it were a well, let's see, it's not a standard aluminum electrolytic. Closest thing would probably be the chart for the dipped solid tantalum capacitors. So if we look at the chart, the lowest value is 1 microfarad, and the highest voltage is 1000, and it would actually 11 microamps would be permissible, so that's interesting. So even though it's showing higher than the other one, it still probably falls within range. Retesting now, it's a little bit higher now, 1.32 microamps. Let me look at the other one. Value checks out. Leakage 0.85, 0.82, and dropping 0.74. Yeah, this one seems to be better. Yeah, so I would say that this other one here with the 1.2 whatever is pretty suspect. So I've either got a problem not capacitor related, because these 2 capacitors right here that I took out of mine seem to be actually testing fine. Either that, or they're breaking down under the high voltage that they're being subjected to, or I've got something else going on here. I think I should take a look at that coil. So let me talk about that coil. I keep saying coil because it looks like a coil to me, but this is that transformer that I've been calling a coupling transformer. So basically we've got this big lug connection here where the main welding power output is connected to this, and then down the other end, this lug right here is actually what's connected to the back side of the large cable going over to where the electrode hooks up. Okay, so the heavy current flows through this metal coil. Okay, but what they did was they bent this metal coil into a channel. Okay, and then they took this wire right here and they laid it inside that channel. So you can actually see inside there, that's actually this wire. So what you've got is you've got a wire wrapped around this metal channel coil. And by doing that, effectively what you've got is you've got a transformer. So naturally these smaller wires here are what the high frequency is being sent out to. Okay. So this device right here, if these spaces in here, these air spaces, get all filled up with trash and garbage, it might be enough to to actually stop that coupling action. So I think we should open up the case and see what we got inside. Well, it's kind of a tight squeeze here, but we're going to try and get in and get a look at what's going on inside here. So there is our coupling transformer, or whatever you want to call it. We all know what it does. We talked about it. Okay, there's a bunch of garbage on top of that transformer. There's a lot of cobwebs and crap over here. Okay, same thing up on the top, dust and garbage. There's even some cobwebs and some stuff on that coil itself. That's the rheostat, which acts as the intensity control for the high frequency. Those connections have a little bit of corrosion on them. They seem tight. And there's even some cobwebs and stuff down over here. And that connection there is a little bit of corrosion on it. So I think what I'm going to do now is maybe I'll fire this up with it nice and dark back here and see if we can't see any high frequency trying to bleed off somewhere. But first I have to put my capacitors back in. Alright, I didn't see any signs of anything inside there as far as any arcing or anything. So now I've decided to go back and try removing one of the two capacitors to see whether or not one of them is breaking down. If I'm lucky and only one of them was the cause of the problem, then by having just one in circuit, I should see an improvement. And then I'll know that that capacitor, even though it tested okay, out of circuit is breaking down. So let's fire this up with one capacitor in and see what happens. If anything, that looks even weaker. The spark gap activity looked even weaker. So let's see if I switch that one out with the other one, whether or not it's the same. All right, it's been a few days since I've worked on this thing, so not quite sure where I left off, but apparently the last thing I was trying to do was I was trying to swap out different capacitors to see if one or the other capacitor alone would make a difference, or if one of the capacitors that I had from the other machine would make a difference, and none of that seemed to do anything to improve the situation, which means that either all of my caps are bad and breaking down under high voltage, which is possible, or something else is going on. So I decided to take out, because I got a lot of connections here that have corrosion on them. So I decided to undo some of these connections and clean them up. And also I wanted to take out this coil right here, which actually is the, again, I'm calling this thing a coupling transformer because of the type of job that it does. I unbolted the coil, and there's a lot of corrosion and everything on it. I want to get it out here on the bench and get a better look at it. And I pulled it down out of the way, and that exposed that beast right there, which, because of where the wire, I just traced the wires, that's clearly the high voltage transformer for the high frequency circuit. So those two black wires on the top are the primary windings, connect to that. So that's going to be the 120 volts that comes in. And then the secondary consists of that wire right here, okay? And then there's another one right here that comes over, and it actually shares a connection. There's two I connections. They're actually stuck together. So the bottom end of this coil right here is actually tied to the one of the leads of the secondary. The other lead of the secondary goes through a hole in this red fiber board out through the front to the capacitors in the spark gap, which makes sense. So my problem right now is, in order to remove this completely from the machine, I've got to I've got to undo, it looks like that might be just electrical tape, I'm not sure, that they bound the two of those together, and then I just got to pop those two connections apart. Hopefully they're just going to come apart. All right, so that's some really dried electrical tape there. That was easy to undo. And then that eye connection, that eye terminal actually did pop off the other one. But now that I got this out, I want to get back to looking at this transformer. This transformer has a lot of corrosion on it. Part of me is thinking, boy, I wonder if the transformer could be part of the problem. But I tend to want to think that because I have activity at the spark gap, that high voltage is coming out of the secondary of this transformer. So that makes me think it's not going to be the culprit. However, could I have some shorted turns in the secondary of this transformer which would lower the output? So in other words, could it be producing less high voltage than it's supposed to? And of course, I have no specs on this, so I couldn't, even if I did have an AC kilovolt meter, I couldn't really get an accurate reading on this thing anyways. The only thing I could do is I could take, if I had the specs, I could get a resistance measurement of the secondary and see if it falls within spec, but I have no idea what that should be. As far as replacing this transformer, my understanding is that this there is a transformer that is used in, I think, some later dial arcs or synchrowaves that actually can be used to replace this transformer, but it's not cheap. I'm really wishing I had kept the transformer from the unit that I scrapped, but I don't think I did. So the reason why I'm thinking I really wish I had kept that transformer from the other unit, because the other unit I scrapped, I think in many ways was in better condition. This is the coupling transformer from that one, and you can see it has virtually no corrosion on it. It still has this almost like a shellac. You can see an area where I scraped it off right there because I was trying to see what kind of metal this was. It appears to be aluminum. But this one, I mean, it's filthy for one thing, but it's also got quite a bit of corrosion, and there's a lot of dirt in there too, and that dirt doesn't help things, by the way. So, all right, so I cleaned up the these connection areas on the coil here. They're nice and shiny metal now, and so I'm ready to install this coil into my Airco. And the other thing I had to do is I had to put new ring terminals on because the hole size on the terminals that were on here was actually too small for the studs that are in this unit. Other than that, the coils were identical. So I'm cleaning a lot of these connections, and then I happen to see this one, and I was like, ooh, that's not a very good looking connection there. There's clear signs of corrosion on that, where this copper strap attaches to this brass stud. Let me show you where that was. So that's the copper strap that actually runs from the spark gap, connects right here, and kind of dog legs and goes down behind here. And this cable right here for the post flow timer kind of obscured it, but I just happened to see it. You see it's kind of in a nasty spot back there to get to, so I just figured I'll just take it out completely, clean it really well, and put it all back in. And I'm going to do that to all of these connections. Well, here's another bad connection. This is the Rheostat, which is also the high frequency intensity control, but I don't think this is the cause of my problem, because when I turn it all the way up to max, it does read 0 ohms, which is what I would expect. So full throttle it works, but I did notice that as I turn it down, it doesn't have a nice smooth change in resistance like it should, so clean that up. I'm even going to clean up this whole spark gap assembly. I had removed these and cleaned these previously. At least I thought I did. Actually, that doesn't look so great. Maybe I didn't. These I hadn't removed. These are the fixed ones that are actually these little Allen screws right here. You loosen them up and you can take these out. And then this is the side that's more easily adjusted by loosening these screws. It opens up the split gap and allows you to adjust that gap. But, you know, any corrosion on these, any oxidation, which you can see there's heavy oxidation inside that brass block that they sit in. You know, yeah, might not make up for a hill of beans, but. And then I can also clean the faces here a little better by having them completely out, as opposed to just trying to stick like emery paper in between the gap there. Well, those cleaned up nice. So to clean these bores, I just wrapped a little hunk of steel wool around a small rat's tail rasp, and just stick it in there and spin it like crazy as I push it through. Okay, I've got everything put back together, rewired, cleaned up. I regapped these to 0.008, which is what the manual says to do, and there was a sticker on here somewhere I remember seeing that also said 0.008 was the gap. A couple of people I think had mentioned in comments on my videos, and I've also seen comments in other posts saying that if I increase the spark gap, that I'll be able to increase the high frequency output even higher. So I toyed with the idea of doing that. I guess the max is like 0.012. But my concern with doing that is, my whole thought process was, if 0.008 is what it was designed to work at from the factory, why isn't it working now? Now, could it be that I need more high frequency, I need to gap it more, get more high frequency output to overcome the leads and the water-cooled torch? Well, this was designed to work with a water-cooled torch though, so that kind of makes me think that that's not the case either. So for the time being, I'm going to start with the 0.008. If I still can't get my high frequency to work at the torch end, I'm going to try regapping this and see what happens. But let's see whether or not cleaning up all these connections and doing all this other stuff did anything. Because if that doesn't work, and regapping it doesn't work, then I'm going to have to go on the assumption that there's a problem with these capacitors. So I'm just going to do a quick test. We're just going to fire it up, close the contactor, and see if our spark gap action looks, is working. If I don't get any spark gap action, then I probably put something together wrong. Boy, is it just me, or does that look a lot more intense than it was before? Well, I think that is a lot stronger than it was before. A lot of that was almost like a scratch start, but I think I could just see the tiniest faint little spark right before I touched down. So I don't know. I'm gonna regap the spark gaps to 10 thousandths and see what happens.